Good morning. Today we are going to continue with the exercise 5.1. We have already done and discussed till question number 13, and I hope you all have completed your work till question number 13th. So let's start with question number 14th onwards. Now, according to question number 14, we have to discuss the continuity of the function fx equal to 3 when x lies between 0 and 1. It is equal to 4 when x lies between 1 and 3, and it is equal to 5 when x lies between 3 and 10. Now here clearly the function is defined in a closed interval 0, 10. And now we'll just quickly do a recap of how we decide continuity in a closed interval. Now we know that a function f is continuous, and we'll be writing CTS to indicate continuous function. So a function f is continuous in a closed interval AB if and only if, first thing, it is continuous at all points in the interval, at all points in the open interval AB, that is when x lies strictly between A and B. And second one, it is continuous at x equal to A, and it is continuous at x equal to B. Now let's see how this function is defined in this interval 0 to 10. We can clearly see from the definition that it's not only defined in a closed interval, but within this also it is defined in a different manner between 0 and 1, in a different manner between 1 and 3, and a yet different manner between 3 and 10. So this interval 0 to 10 is further divided at two more points. One is 1 and the other one is 3. So in order to check the continuity in the closed interval 0 to 10, we have to check the continuity. So to check the continuity at x equal to 0, at x equal to 1, at x equal to 3, and at x equal to 10. This is the first thing which we need to do. The next is that to check the continuity in three intervals. One is when x lies between 0 and 1, another one when it lies between 1 and 3, and the third one when it lies between 3 and 10. So when x lies strictly between 0 to 1, x lies strictly between 1 to 3, and x lies strictly between 3 to 10. So let's first discuss the continuity in each of these three intervals. So as we can clearly see, when x belongs to open interval 0, 1, then what happens? That is, x lies strictly between 0 to 1. By definition, we know that in this interval fx is defined as 3, and so we will have fx is defined as 3, and it implies that f is continuous being a constant function. Okay, now we check when x belongs to the open interval 1, 3. that is x lies strictly between 1 and 3. By definition, fx equal to 4. Again, f is continuous, being a constant function. Next, again, when x belongs to the open interval 3, 10, that is x strictly lies between 3 and 10. fx is defined as 5, which implies that f is continuous, being a constant function. So we have seen that in each of these 3 intervals, the function is continuous. Now let's check the continuity at each of these 4 points. So first, let's check at x equal to 0. Now we know that the function is, there is no portion of the function on the left side of 0. And so to check the continuity of the function at this point, check the continuity, we have to check, we have to show that the right hand limit is equal to f of 0. That is limit x tending to 0 plus fx is equal to the value of the function at x equal to 0. Now for that, what we do is, so let's start with that. So at x equal to 0 we are checking. So first of all, we'll check the value of the function at x equal to 0 is 3. Let's call it equation number 1. Now to check right hand limit. So limit x tending to 0 plus fx is equal to limit x tending to 0. We drop this plus sign, write the definition on the right of 0, which is 3, and this comes out to be 3. So 1 and 2 implies that right hand limit is equal to value of function at x equal to 0, which implies that f is continuous at x equal to 0. Next we check at x equal to 1. So f of 1 is equal to 4, f of 1 is equal to 3 by definition. So let's call it equation number 1. Now here we can check both right hand limit and left hand limit. So let's first do the left hand limit. Limit x tending to 1 minus fx equal to limit x tending to 1. We drop the negative sign, write the definition on the left of 1, which is 3. It is equal to 3. So what we get is, therefore 1 and 2 imply that left hand limit is equal to value of the function, which is equal to 3. Now right hand limit, limit x tending to 1 plus fx, limit x tending to 1, we drop this positive sign, write the definition of fx on the right side of 1, which is equal to 4. So let's call it equation number 3. Therefore 1, 2 and 3 imply that left hand limit is not equal to right hand limit, and therefore from 2 and 3 we will check. So is not equal to this, therefore limit x tending to 1 does not exist. Therefore, there is no question of checking the continuity at x equal to 1. So we conclude f is not continuous, or we can say discontinuous at x equal to 1. Now let's check at x equal to 3. F of 3 is equal to 5. Call it equation number 1. Left hand limit x tending to 3 negative fx is equal to x tending to 3. We drop the negative sign and replace the definition of fx by definition on the left of 3. On the left of 3 it is 4. So the answer is 4. Therefore 1 and 2 imply that left hand limit is not equal to f of 3. Right hand limit x tending to 3 positive, limit x tending to 3. Definition on the right side of 3 is 5, which is equal to 5. Therefore 2 and 3 imply that left hand limit is not equal to right hand limit, which implies that limit x tending to 3 of fx does not exist, and therefore f is not continuous at x equal to 3, even though the right hand limit is equal to the value of the function. But still, since the limit is not defined, we say the function is not continuous at x equal to 3. Now we come to the last case, that is at x equal to 10. Now clearly we know that there is no definition of the function on the right of 10, and so we will only check the left hand limit and the value of the function at x equal to 10. So let's see, f of 10 is equal to 5. The left hand limit x tending to 10 minus fx, limit x tending to 10, we drop the minus sign and we replace the function by definition on the left of 10, which is 5. It gives us 5. 1 and 2 imply that the left hand limit is equal to the value of the function at f equal to 10, and therefore f is continuous at x equal to 10. Now from all these cases, thus we conclude that the given function is continuous at all points of the closed interval 0,10 except at x equal to 1 and at x equal to 3. Okay, similarly we can check the continuity of other questions in question number 15 and 16. They are also in closed intervals, and can be done on the same lines as question number 14. So I will take one more question of this kind, which is question number 16. It is partly closed and on one side it is open. So let's check that. So fx is defined as -2 when x is less than or equal to -1. It is defined as 2x when x lies between -1 and 1, and it is equal to 2 when x is greater than 1. Now clearly the function is defined for the interval which is semi-closed, that is less than or equal to 1. So it is basically defined in for all real numbers, but with the condition that there is a different value on the left and right of x equal to -1 and different value on the right and left of 1. So here it is basically the question which is defined on the real line. So we divide it into various intervals like x less than -1, x lying between -1 and +1, and x greater than 1. Then at x equal to -1, at x equal to 1. Okay, so let's first do the three intervals when x is less than -1. Okay, so here we have, there is only one definition which is -2. It is f is continuous being a constant function. Then when x lies strictly between -1 and +1, fx is defined as 2x, which is continuous being a polynomial function. And then the third case is x is greater than 1, fx is again a constant function, and so it is continuous being a constant function. So in all these three intervals the function is continuous. Now checking at x equal to -1 and at x equal to 1. Now at x equal to -1, let's first do the value of the function at -1 is equal to -2. Now left hand limit x tending to -1 minus is equal to limit x tending to -1. We drop this negative sign, replace the definition of fx on the left of -1, which is -2, which comes out to be -2. Now right hand limit x tending to -1 plus, we drop the positive sign, replace the definition on the right of -1, which is 2x. This comes out to be 2 into -1, which is -2. Clearly left hand limit equal to right hand limit. Therefore the limit as x tends to -1 exists and is equal to -2. Also the limit is equal to the value of the function at -1, and this gives us f is continuous at x equal to -1. Now let's check the continuity at x equal to 1. F of 1 is equal to, now here it is, f of 1 is equal to 2 of 1, which is equal to 2. Now left hand limit. Limit x tending to 1 minus fx is equal to limit x tending to 1. We drop the negative sign, replace the definition of f on the left of 1, which is 2 of x, which comes out to be 2 into 1, which is 2. Right hand limit. Limit x tending to 1 plus, which gives us limit x tending to 1, and definition on the right of 1 is 2, which is 2. Clearly left hand limit equal to right hand limit. Therefore, limit of the function as x tends to 1 fx is defined and is equal to 2. Now also limit x tending to 1 fx is equal to value of the function at 1. It implies that f is continuous at x equal to 1. And thus we see that all these things, we see that the function f is continuous for all values. In fact, all values in real numbers. Okay, on the same lines you can try 15th question and similar questions. Thank you.